All right. Good morning. A nice and early, crisp morning. Hopefully you are all enjoying the view. Thank you for joining us for this IREP event. It's been 5 long years since we last met in Porto with Joao. Thank you, Joao. It was a wonderful event. Hopefully this will be as good or if not better than Porto. So we are going to be having these presentations. We're going to be having these presentations, these events, I guess, these sessions for about a couple of hours. I guess Hamid is going to explain the procedures. I just wanted to make you aware that we are taping the event, okay? So if you have any objections, let us know. Hopefully there aren't any. The reason for that is because we prepare, part of the IREP, as probably most of you know, is a discussion, right? A discussion happens, it's basically a panel. And we leave the presentations are relatively short, and we spend more time discussing the papers, and we prepare a summary of the events, a summary of the discussions. The chair and secretary of the sessions prepare that, and so we'll ask you to basically use your the microphone. Okay, stand up and reach for the microphone if you have a question, comment, or discussion to lead. This is a very informal meeting, as you already noticed. Okay, some of you are wearing shorts, which is fine. I guess we welcome that. This is not a very formal event. We do have a social gathering as well. It's more to, a gathering of friends. That's the way it's been all the time. We keep it that way. So in that regard, we're not going to have formal introductions, bios, or any of that. Just your name and where you're coming from. And if you want to make your own introduction, your own time to do that, you're welcome to do so. Otherwise, we'll keep it very informal, mostly first names, as much as possible. So with that, I guess I'll let Hamid explain how this is going to work. Thank you.
Thank you, Claudio. Good morning, everyone, and welcome to Banff. So you can see that when the weather goes above 20 degrees, it's summer for us. And it's really hot here. So for the papers, we have scheduled 5 papers per session. There are a few sessions that have 4 papers. We have 3 speakers who, in the last minute, had to cancel because of visa issues or COVID issues. So we've arranged for them to make an online presentation. Each presentation, we are hoping that you can stick to the time, 15 minutes, 3 minutes, 1 question after each. And then after all the presentations are done, we will have a panel discussion. So we ask you please to stick around. The area is not probably wide enough for like 7 people, but hopefully we can squeeze in and sit there. And because we are taping, please make sure to use microphone. If you prefer to walk around when you talk, use this, please. If not, use this. And then when you're sitting there, we have microphones, so please use microphones. The chairs and the co-chairs will be preparing a summary of the key points and discussions, especially the panel discussions after. And we are hoping that they can give us the panel discussions before lunch today. No, I'm kidding, of course. But, it's the sooner the better. And we are publishing those discussions. It doesn't have to include the names or, but the summary of key points mentioned. And the last thing is that please make sure to bring your slides on a USB or somehow and introduce yourself to Armagon. Armagon is going to set everything here so we don't have transition time. And also, those who are presenting, please introduce yourself to the chair and co-chair of the session beforehand so they know who is presenting. And take 5 seconds, 10 seconds to introduce yourself. That's it. Thank you very much and enjoy the show.
Okay, good morning. Welcome everyone to our first session, which is called Communications and Cybersecurity. I am Antonio Simões Costa, and together with my colleague Gregor Verbich, we'll be chairing this session. We have actually the pleasure and the privilege to chair the very first session of IREP 2022 symposium. And Hamid already gave us all the instructions. And then we call the first paper, which is called Implementation of Machine Learning-Based DER Local Control Schemes on Measurement Devices for Counteracting Communication Failures. The authors are Rajkumar Palaniappan, Jan Niklas Sesklau, Stavros Karagianopoulos, and Christian Rettant. The authors are with Dortmund University, TU Dortmund University in Germany, and the third author is also with Swissgrid in Switzerland. So, please.
Thank you. So, good morning, everyone. My name is Rajkumar Palaniappan. I know it could be a difficult name for the Westerners. Raj, it's simpler. I come from the TU Dortmund University. Christian Rettan should have presented the paper, but fortunately, I got my visa on Friday, and I flew through here yesterday, or day before. I got up here at 3:30. I don't know if it was jet lag or if I was just excited to be the first presenter of the entire conference. So my paper is, in theory, just to use machine learning algorithms on hardware devices in the field, in distribution grids. So for the motivation, we all know why we are here. For the electrical industry is changing drastically, active grids and passive grids, smart grids. And let me not waste too much time on this one, but one point, we need to have more devices in the field so that we can communicate the the measurements or the system states at a central level to the control center in a distribution grid. In transmission grids, it's already available, but in distribution grids, it's already not the same. So what are the challenges for distribution grid automation? As I said earlier, in transmission grids, the system is completely different. There's more automation. In distribution grids, it's not the case. We can ask, okay, why not just transfer the entire ideology to the distribution grid? We do not have enough measurements. Of course, we can make enough measurements, but then it's going to cost us. And even if we are ready to make measurements, we have spatial constraints like these. And here you can see that our colleagues are trying to find the handle of a cable distribution center, and these are the practical difficulties that we cannot have measurements at every place that we want. And the state of the art, so what we are trying to do with the distribution grid automation, HV grids are already there. No measurement or automation in the distribution grid, and of course, we are not the only ones to deal with this problem. There are a lot of solutions, and of course, these are not the only solutions. These are the ones that we found out. The only problem with these functionalities or these devices or these implementations are that all the solutions are unique, which means that each device has a particular functionality. Say, for example, I go to ABB and I get a protection device. They give me a protection device for, I don't know, distance protection. And then I need another device for differential protection. So it's not a plug and play mechanism. It's not modular in that sense. So what we can do for that modularity, so the separation of hardware and software is kind of important. And there comes the need for IEC 61850. So what it means, you can make portable software which is independent of the hardware. So I can use software from any vendor, and I can just select one hardware which is capable of sorting out the requirements, and then easy integration of new application from other vendors. I'll tell you in a bit what I mean with this. So, which leads us to the research questions. With the help of distributed measurements. So it's kind of clear that we need to have distributed measurements, but with the help of these distributed measurements, how can we use 61850 data standards to have a separation of hardware and software? And the second one, system and communication failures are inevitable. We cannot go around that one. So how the control algorithms can be implemented as robust as possible to counter these failures. And the last point, of course, every machine learning algorithm or every device is only as good as the training set, so it has to be periodically and dynamically updated. So these are the particular questions that I dealt with in this particular paper. So coming to the implementation part, a short history of the development process. So this is not a process that got up in a week or overnight. So this is a process which has been happening for the last 10 years. In 2012, or just earlier, Christian and the other colleagues decided, okay, every protection device is a device, or every protection functionality, I need a device. So why not separate hardware and software? So in the project iProtect, they have, or my previous colleagues, they implemented protection functionalities on a Beckhoff PLC. So all the protection functionalities, distance differential, overcurrent protection, they implemented on a Beckhoff PLC. And then we went one step further with iAutomate. So once the protection functions were there, then we decided, okay, why not also control functionalities? Then we have a project partner which is called COCOS in Germany. So these are power quality measurement devices. So because it has power quality measurements, it has a high frequency of measurements with which I can use my protection algorithms on top of the existing functionalities. So with these devices, we also made sure that we implemented control functionalities. And the next project, we went one step further with iAutonomous, where we use functional containers for each of them. So for example, state estimation is a container using Docker Kubernetes, and the other functionalities can make use of this containers. So it is not dependent on one application. Every application can use of the containers and can talk within each other or amongst each other. So a typical implementation. So let's say, take for example, the optimal power flow. So here I have two field devices, and these field devices communicate with the measurements to the controller device, and this control device is typically at the central substation, at the secondary substation, 110-20 kV. And it has the overall system state of the entire grid, and it can send out the OPF set points for the DERs to be connected. So pretty simple. But what happens if there's a communication fault, or if there's an electrical fault at the controller IED? There's no communication, and the field IEDs have to act independently. So what is the what is the conventional fallback solution? They go back to Q of V control, which might not be the ideal case circumstance. So what we went ahead and said, okay, why not emulate the central OPF in the particular IEDs itself? So the IEDs have to be robust enough, or the IEDs can have a regression algorithm. So just as a rule of thumb, we started with the easier options, the piecewise linear regression, and the nearest neighbor regression. Again, these are not the best regression algorithms, but we wanted to check if at all I can implement machine learning algorithms on the hardware devices, and we were able to. And that's the reason we started with the easiest possible regression algorithms. Again, it's the same with the optimization function itself. We use simple math power optimization. Here's the control, the cost optimization, and then I have a dead band in the middle so that I don't have to control when I'm near 1.0. I can maneuver these values, and then I can play around with this ones. As I said, these are just exemplary implementations. And there are three important factors. The three scaling factors, I have PV, wind, and load. So again, for simplicity, I reduced everything, the complexity. So PV has a scaling factor, wind has a scaling factor, and the loads have a scaling factor. And these scaling factors are scaled from 0 to 100% in 5% steps, which means I have 21 steps. So 21 steps, power 3, I have 9,261 different combinations for all the OPF possibilities. So that's where I have here 21 different data sets for P and Q set points, which leads me to 42 different data sets. And the initial regressions are loaded into the field devices, and then this entire setup is validated with the hardware in the loop test setup. So during normal operation, the central controller IED gives me the set points, and then it is transferred to the DER. And the initial regression is already there in the hardware device itself in case of emergencies. And when the central operation is not there, the hardware device feeds in the input of the actual voltage, actual nodal voltage, and then the actual P max of the DER, and it gets back the P and the Q set points from the regression algorithms. And here you can see that I can update the P and V and Q whenever the training sets are not the same. So we tested this one in a Seagram medium voltage grid, again, exemplary grid. We later, in retrospect, we found out that this was not the best solution. So this was not the best option. I'll tell you why. This is kind of a benchmark grid. So I did not have that much options to maneuver my voltages and my loads in this particular case. So I should have gone with a better grid. But let's say, for example, that we have multiple DERs. I selected 2 of the DERs in each of the, so 1 DER in each of the branch as controllable DER, and I attached my field device onto this particular DER. And these devices send me the values of the central, send me the measurements to the central controller, and the central controller gives me the outputs or the optimal set points. This is what the controller says, or the validation setup looks like. The real-time simulator sends me the local measurements to the field devices, and the field devices send it to the master or the controller IED. And then you do not have enough possibilities to have every device as a hardware device because you also have hardware restrictions. So some are simulated virtually, and then the virtual commands the virtual measurements are also sent from this real-time simulator directly to the controller device. So these were also done. So the results of the various control strategies. So I tested 4 strategies. One with the black version, where the black curve, which is no control, the green one, which is regression control, the blue one, which is OPF, and the red one, which is the Q of V control. And here, the various blocks here, the green ones are where communication is intact, and the red or the pink, whichever we can see, is where the communication is blocked out, which means that the regression algorithm should take preference. And in ideal case circumstances, the green and the blue curves should overlap each other. So that would be the perfect case scenario. And we went again and played again with it. So here I simulated a scenario which explicitly was not within the training data set. So here I can see that the centralized OPF would have behaved differently rather than my emulated OPF or the machine learning OPF. And here I can see that the differences are also here in this case of P and definitely in case of Q. But I can see here that the conventional Q of V control is going to be definitely bad than expected. And again, this is just an exemplary grid with one DER. And if this is going to be scalable, so if we are doing it with multiple DERs, with multiple devices in the field, then the expected results is that the number of devices or the central communication need not be responsive or need not be required, and you can have this implementation on every field device, so you need not depend on communication at all points. It's not the best case scenario, but it's still an option to reduce the number of communication required or the number of data required to be sent all around the grid. So, as I said earlier, any machine learning algorithm is only as good as the training data set. There are going to be circumstances where the actual situation is not directly concurrent with the training data set. So what do we do there? We use a periodical retraining. And whenever there's a training data to be updated, the training data the regression models are updated, and then the results are compared. So I have a basic comparison here. As I earlier said, how long do I have?
4 minutes.
Perfect. I can show the devices, the regression algorithm are dynamic. So as the secret grid is not the best case, so is a benchmark grid, so I cannot play with it around. So what we did, we changed the cost parameters. So because of the cost parameters, I have variation in the training data. One can say, okay, this is not the best control algorithm because your control parameter, so your regression algorithm is going to be so deviant, it's not the best control algorithm. I agree. Again, on the other side, from 59.7% to 58.2%, it's not going to be that much of difference. And in any case, my grid is not going to be so drastically changing that I have to change it at every point of time. So this is just to say, okay, if at all there is a drastic change, my regression algorithm can catch up with the dynamic changes. So that's what the idea of this implementation is. So coming to the summary and outlook, as I said earlier, so the control algorithms or the regression algorithms are not the best case strategies. So the idea is separation of hardware and software, usage of 61850 data models, and to have one device which can do everything. So because this device, at least what we have, is a power quality measurement device, this device can do protection algorithms, control algorithms, and exemplarily we tested with machine learning algorithms too. So as we see here, it is possible. So if we want to extend the algorithms, of course we can do it. And one final point that I missed or that I did not do, I tested the algorithms or I validated the algorithms only using a real-time simulator. If I do it with a real grid where synchronous generators and other hardware devices, I'm not really sure how it's going to behave. And that's what the next step is. So we are going to test it with synchronous generators to see how the performance is. And the real-world control is going to be possible only when real-time control of DERs is possible. I know from Germany that P control is only like 0, 30, 60%, and 100%. And if I go to a network operator and say, okay, I want 58.3%, he's going to laugh at me. So this is possible only when real-time control of DERs is possible. And the trial and error method, one important point, the cost parameters were just trial and error methods. So in ideal case scenarios, I have to have another optimization to find the cost parameters and then to use those cost parameters to the machine learning algorithm. This is an exemplary implementation. Everything worked fine. Further works have definitely to be done. Thank you so much.
Thank you, Raj. We have time for one single question from the audience. Well, I have a question to you, Raj. In order to use the proper trained data set, you need to identify the state of the condition, the operating condition, the right. So you are assuming that the communication failure doesn't affect the state estimator. You know what I mean?
Yes.
Yeah.
If it's going to be a if there is going to be a communication failure, I can only assume that there's not going to be that much of a state variation so that the system state is going to be drastically changed. That is a question for a different day for if there's going to be a communication failure and at the same time there's going to be a huge drastic change in the system. Better algorithms have to be designed, but my algorithm is not capable of doing that. I just assume the system state is going to be a similar one, but in any case, I can have the system local voltage, because that's going to be my input for my machine learning algorithm. So if the system state is drastically changing, I still have my local voltage, which I can measure in the system at my particular locally. And using that one, I can only predict, I can only assume that there's not much change, but the overall system is going to be, if the overall system is going to be different, then the algorithm has to be much more complicated.
Okay, thank you. Then we move on to the next paper. Second paper, the title is Assessing the Impact of Cyber Attacks Manipulating Distributed Energy Resources on Power System Operation. The authors are Philipp Linartz, Alexander Winkens, and Andreas Ulbig. They are with RWTH Aachen University, and Philipp will present the paper, right? Philipp, please.
Okay, so good morning everyone from my side. Since we are quite informal here, I'm Philipp. I'm working as a research associate and PhD student at RWTH Aachen University. I'm in my 5th year, and today I want to present you our research on assessing the impact of cyber attacks manipulating distributed energy resources on stable power system operation. Short disclaimer beforehand, though we are in a cybersecurity session, this is more of a motivation for this research. I want to make a deep dive into cybersecurity. And the second disclaimer, of course, 15 minutes are quite not that much time, so I will just show you exemplary results. But of course, you're invited to look into the paper. So I want to take you through our thought process, and I want to start with the motivation a bit. The main important topics here are, during the last years, we have an increasing number of cyber attacks, which of course pose an increasing threat to the operation of cyber physical systems. That means also power systems. We already had a successful attack where an attacker gained access to a grid operator control system in Ukraine back in 2015, which led to serious disruption of services. So, of course, the power system as critical infrastructure has to be resilient against cyber attacks. On the other hand, I'm sure many of you know, we have the increasing number of installed power of distributed energy resources in the distribution grids, mainly renewables, and also their growth is expected to continue. So to monitor and control these assets, we need to deploy ICT. Also, we needed to utilize the flexibility of the DERs for operational or market purposes. So we have in total an increasing number of remotely controllable actuators in the power system. So now we take on the view of an attacker. So the question here is, what disturbance can an attacker achieve by utilizing this flexibility of the DERs? So the goal of this research is to assess the impact of cyber attacks manipulating DERs on power system operation. There are the 3 questions I want to answer today with this presentation. So what are possible manipulation scenarios utilizing the DER flexibility to disturb power system operation? Which metrics can describe the severity of the manipulation scenario? And in the end, which recommendations for DER and power system operation can be derived in order to limit the impact? So the first thing to do is look into actually the requirements for DER operation. So they are specified, of course, in grid codes for DER integration. We did the analysis on German grid codes, but the topics they address are quite similar, for example, to IEEE 1457. So it should be familiar for you. So what do they specify? Of course, permissible voltage and frequency bands during steady state operation and disturbances as indicated in the figure here on the top. Specifies active and reactive power operating ranges and also requirements for static and dynamic grid support. And they also specify how to apply new active and reactive power set points as indicated in the figure here on the bottom. So if the DR receives a new set point saying from 0 to 1 per unit of active power injection, then this kind of ramp applies here, which limits actually the slope of the rise. So it takes around 150 seconds for the new set point to be reached. For reactive power, it's a bit faster. It's within, let's say, 20 seconds and with this kind of exponential behavior. Also, plant protection requirements are specified there so that if for example, the voltage is outside the specifications of the voltage band, the DR should disconnect after some specified time. In addition, there are also requirements for the data points transmitted between DR and central control. Of course, monitoring and status signals, and on the other hand, control signals. For example, the active power set point, the reactive power set point, and disconnection commands. So rather straightforward here, we want to use the control signals to create a disturbance as an attacker. So we say our cyber attack is somehow a control-based attack targeting the integrity of the control commands. And if this kind of attack is successful, the attacker can communicate with the DRs, of course, within the specifications of the communication protocols that are used here, and also, of course, just using the data points that are already specified, so the kind of control commands I showed you on the last slide. To make this, to handle this, we made some fundamental assumptions. We said all DRs at medium voltage level and above are connected to the grid operator control system via the process control network. This is, let's say, a valid assumption for future scenarios because at least the most recent grid codes, they already require it. We say the attacker has sufficient knowledge of the control system and the process control network to send valid control signals to all connected distributed energy resources. You can imagine this kind of cyber attack, they're usually multi-stage cyber attacks, so the attacker usually is in the system long before he actually performs the action in the end. So he did some reconnaissance and has the knowledge actually to forge this kind of control signals. Then the third assumption would be the grid operator cannot react immediately since the attacker is somehow in the control system or in control of the control system. And the fourth assumption would be though the central control is somehow compromised, the local plant control and the protection of the DRs is not compromised. So if the set points, for example, are sent to the DRs, they will apply them within the specifications of the grid codes as I've shown you on the last slide. So since we're not so much focusing on the interdependence between the cyber and the physical system here, we simplified the modeling, basically modeled the electric power system and its assets, control circuits, protection functions, and so on. And we just added some interfaces for the control commands. The next question then would be, what are the manipulation scenarios I'm looking into here? So what does the attacker want to deploy in the end? So we said the aim is somehow to violate the voltage and frequency band to cause some kind of cascading effects or maybe even cause some stability issues. So we went on and defined 3 generic manipulation scenarios with different targets. So the first one would be the undervoltage manipulation scenario, where the goal of the attacker would be to create undervoltage situations. Therefore, he sends a new P set point of 0 to all connected DRs and a new Q set point for the DRs to actually absorb reactive power, which even more decreases the local bus voltage. The second scenario, just in the other direction, the overvoltage scenario, where he just sends new reactive power set points to the DRs so that they inject reactive power, which increases the bus voltage. Since we are assuming that all DRs will operate at maximum active power injection anyway, there is no way he can send an additional active power set point, which would have any impact there. Both come in 2 variants, which are just distinguished between the limit of the reactive power injection, and then there's the disconnection, which is just the synchronous disconnection of all connected DRs. Next question would be how to assess the impact of these manipulation scenarios. So we defined a severity index based on voltage band violations and plant protection triggering to assess the local impact and the cascading effects. It is shown here on the right, the severity index. An index of 0 indicates a non-critical scenario. An index of 5, it's a highly critical scenario. And the criteria would be the deviation from the voltage band and how high it is during the manipulation and even in the new steady state. And the other criteria would be this kind of how many, or are there other DRs who are tripped due to the bus voltage violations, for example. These are the kind of criteria. In addition, we also looked at the number and amount of lost active power injection of disconnected DRs. So then we used these manipulation scenarios and these assessment criteria to perform a case study. So we have two distribution grid models, both containing the high voltage and medium voltage level. As you can see here, they both come, so this is one grid model, this is the second one. They both come in three, so to say, scenarios for today and to future scenarios. So we investigated for each grid model, we investigated all the manipulation scenarios and also different initial study case or operating points, which somehow are used to show the different initial operating points, for example, high load situation with no generation, distributed generation in feed, or low load situation with high distributed generation in feed. So for each of these scenarios, we performed a dynamic time domain simulation to actually apply these events and look at the results, for example, bus voltage or frequency. And the key findings here are the severity, of course, increases for future expansion scenarios. Why is that? It's quite simple, since we said here that the attacker is able to utilize all wind power plants. In the future scenarios, there are just more wind power plants, so the attacker has more flexibility to utilize. Then the overvoltage manipulation scenarios have an increased severity for the low load and high generation study cases, since the initial bus voltages are higher in the beginning. Vice versa for the under voltage manipulation scenarios, since the bus voltages for high load study cases are lower in the beginning. What you can also see here, if you compare these manipulation scenarios, they have an index of 1 or 2. 2 is the one with the higher limits of reactive power provision. If there's a higher reactive power provision possible by the DRs, then the scenarios are more severe, since the reactive power has a huge impact on the local bus voltages. Just one brief mention about the disconnection scenarios. So they don't seem that critical with the severity index, but however, they will always lead to the maximum lost active power injection, since if you disconnect all wind power plants, injecting maximum active power, this will always be critical. So the manipulation scenarios actually achieve the voltage band violations, and the protection triggering limitation of reactive power provision will likely decrease the severity. I want to just use the rest of my time to get into one of these scenarios in detail, so that you get an idea of what was actually simulated. So I took one undervoltage manipulation scenario, which ended up with a severity of 4 and lost active power injection of 160 megawatts. The 4 figures here indicate the bus voltages at the EHV-HV substations, at the MV substations, the OLTC, on-load tap changer tap positions, why I will tell you later, and the power flow at the connection point to the bulk power system, or here the extra high voltage level. So the scenario was initially high load and high generation in feed, and then the attacker sent the commands to decrease the active power in feed to 0 and to absorb 0.5 per unit of reactive power. What happens then immediately in the first 10-15 seconds is the bus voltages, they decrease very fast. That's due to the time constant of this reactive power application, which is much faster than the active power anyway. So there are, like, after 10-15 seconds, the first DRs to actually trip due to the bus voltages being too low, even inside these low voltage ride-through requirements. So we end up in this new steady state for some 10 seconds. If we would stay there, after 60 seconds or so, even more devices would disconnect due to undervoltage protection. what happens here, we assume like automated OLTC operation, and they are actually able to bring back the bus voltages within the voltage band. However, I mean, this is a new steady state. However, we have a significant change in the power flow at the grid connection point. As you can see here, within 150 seconds, the active power flow there changes like quite significantly. Of course, this has somehow been provided or absorbed by the bulk power system. And one other thing is we are in a new steady state, but there are still wind power plants connected, which the attacker could use for a second set of control commands, but we didn't investigate that here. So yeah, then I want to conclude my presentation actually. So what we set out to analyze the impact of the manipulated DERs on stable power system operation. The manipulation scenarios we designed led to significant short-term changes in the operating point of the distribution grids within some 30 seconds. Especially the manipulation of the reactive power can lead to bus voltage violation and these kind of cascading effects with at least DER stripping in the distribution grid. Increased DER penetration is more critical. And I want to just point out two countermeasures like, let's say, local control loops not depending on central control, like these automated OLTCs at the substation, if we assume they just measure their voltage at the lower voltage level. And also, yeah, limitation of the amount of Q injection is accessible by central control, either by fixed values, which they already are, so to say, or depending on the bus voltages, so that the DR actually maybe rejects control commands if the bus voltages is outside of the voltage band at the point where it receives. Further work has, of course, to be done too, especially the impact on power system frequency. We had a very simplified model of the bulk power system, just one huge synchronous generator. There must be some additional power frequency control there and some thoughts about the system inertia to actually assess the impact on the power system frequency. And also, I mean, we assumed the attacker, they send the control values to all connected to all connected DRs. You can limit the success there with a probability of lower than 1. And just one final remark, of course, this was more about the countermeasures in the power system, but since we are in a cybersecurity session here, the countermeasures have, of course, to be accompanied by investment in cyber attack prevention, detection, and reaction, so that the attacker hopefully isn't even able to perform this kind of attack. Thank you for your attention. If you have any questions.
Thank you, Philip, for a nice presentation. Questions? One question from the audience? Oh, yes, I have a question. Please use the microphone.
Spiros from DTU. So I want to ask, so why, if you disconnect the DRs, the severity is lower? Just to better understand.
Yeah, because the severity did only look at the voltage values locally. So if you disconnect them, of course you lose the active power injection. It has an effect on the local bus voltages, but not so much as if you would utilize them to inject or absorb reactive power. So in that way, the severity is lower. I do agree with you, however, if I disconnect lots and lots of active power injection, of course I get an issue for power system frequency. But that was not like properly investigated here. That's why I put it in the outlook in the end.
Okay, thank you, Philip. Then we must move on to the next paper. The title is Communication Censored ADMM for Electric Vehicle Charging in Unbalanced Distribution Grids. The authors are all with the School of Engineering, the Australian National University, and they are, I don't have the first name here, but there's Bardvaj, close enough? Close enough. Okay. Carvalho, that I know, De Carvalho, W, Nimau Siri, Rainan, and Rain. So, your name again?
Oh, Abe.
First name, Abe? Mm-hmm. Abe is going to present the paper, the first author. Okay, go ahead, Abe.
Okay, thank you everyone for attending. So I'm Abe, I'm the author here. These are the collaborators of the paper. Yes, my name is also long and complicated and looks like a lot of random syllables with vowels thrown in randomly, so I just go by Abe, and that's perfectly fine. So firstly, my thanks to the organizers, review committees, and so on for looking at our work for thinking it was acceptable, and then for letting me come here to enjoy the mountain views for breakfast. That was incredible and totally worth it. So I'm going to talk today about communication-censored ADMM for electric vehicle charging and coordination in distribution grids. So let me start by saying this. I'm a mathematician. That's why you get the classic Beamer slides. If any of you are traumatized from your undergrad, please don't run away just yet. Give me a chance. And I'm going to take this nice and slow to just talk about some of the problems that we looked at in this work. So here is a standard setup of a distributed electric vehicle environment that we're considering. So you've got someone's house up here, and they maybe have some other sources of renewable power, maybe solar panels, I don't know, what are the HVAC things, or something else. And then they have an electric car that they've just bought, and they want to use that to buy and sell power to the grid, and perhaps make some money from it, or help their neighbors, could be anything. So this is the kind of system that we're considering. And now if you have multiple people with these electric vehicles, you of course need to coordinate your charging and discharging, because if everyone gets home at 5, plugs their cars in, and everyone tries to charge, you're going to get bad things happening. Yeah? Sound about right? Well, what kind of bad things? Well, these kinds of bad things. So here is a curve of voltages at particular nodes and particular times of days. So I think here everyone comes home around 7-ish, and your voltage levels start to go below some pre-specified threshold. Now, this is taken from my engineering colleagues who say that you want to be within this 0.95 per unit system, so within 5% of the nominal. Of course, as a mathematician, it doesn't really matter, right? You can pick your range, and anything's fine. So this is bad, and we want to avoid this. So what we want to do, and in today's talk, what we're going to pretend is everyone here has an electric vehicle, right? You've all driven here to Banff in your electric car, and we need to charge it all. And I'm going to tell you how you can charge it well. So using a consensus-based approach that is easy on communication. Now, I'll come back to the consensus stuff, like why we need consensus. But OK, so let's start with the basic model of our problem, which is understanding how your electric cars work, right? So they work with particular restrictions on the constraints on your actual batteries. So firstly, the power going through your car is limited, right? It has some upper and lower threshold. You can't violate it, because if you do, you might, I don't know, blow up your battery. So we have to be mindful of this. Secondly, your state of charge is also limited, right? And this is something, of course, the user gets to control, because you might say, I never want my car's battery to be below 50%. Always want it to be more. You might also say, I never want it to be above 87%, because I read online that that's the optimal battery health threshold. So that's something else that we need to take care of. Of course, you have your apparent power. So here I'm treating your electric car as just an inverter. So your real reactive power limited by this circle, which is of course nice because the circle is convex, so we like the circles. Whoops. And most importantly, you want to look at the grid voltages when everyone's plugged in, right? So we want to keep these within our pre-specified threshold, which I guess most people assume to be 1.05 and 0.95 of some nominal normalized thing. Okay, so this is my constraint set of an optimization problem that I'm going to make and then try and solve. Of course, it's an optimization problem, so I need an objective. And clearly, I placed the pause at the wrong place, but let's see what this objective is. The one we use in the paper is a pricing objective, right? So it's a simple minimize the cost for each user or maximize the profits for each user if they're selling electricity back to the grid. So here, eta is a pricing profile vector. Essentially, you can forecast what the price of electricity will be and then take however much energy you're selling or using. And now you have this quadratic term, this alpha pn squared. What is this? Well, there's a couple of interpretations of it. So the physical interpretation is that it's a parameter used to preserve the battery health of your car. And that's because if you get rid of this term, your optimal solution is going to oscillate between charge and discharge. So at each time step, you're going to be charging and then discharging, and that's not good for your battery. Now, of course, the other reason this is really good is because this, with alpha being non-zero, makes this a strongly convex objective, which is, of course, great. Now, the reason there was this question mark here is because you don't necessarily have to use a pricing objective, right? You might have different conditions that you're trying to optimize over. Hard to think of any on the spot, but you can have others. Okay, so this is my optimization problem, which I'm going to write down in the standard optimization way, which you guys must all be familiar with, right? This is basically what everyone writes in their papers. So you take your pricing function. I'm going to lump all of my constraints into an indicator function with a slack variable so that, this is 0 if my constraints are satisfied and infinite when it isn't. And then, of course, I get these equality constraints here. And now, of course, I'm doing optimization, and we're living in the modern age, so most of my optimization solvers are going to be some primal dual hybrids, but I'm going to dualize this problem anyway. So this is my dual setup, which, of course, if you want the derivation, look at the paper. I'm not going to go through that here, but I'm going to talk about why this is important. So at the beginning, I mentioned this idea of consensus, right? We want consensus between the users. So why is that? Well, if you don't have consensus, you're really not going to be able to coordinate between everyone, right? Because someone will always say, nah, why should I do this? So why do we use the dual formulation for consensus? Because there is a physical interpretation of this dual variable lambda, which is the price that you have to pay or that you earn, right? So, money is a very good motivator. Oh, do I? Okay, sorry. Okay, we have this dual formulation, and now I'm going to solve this using a classic alternating direction method of multipliers approach, simply because it's a very nice formulation. It fits into this problem, and it has nice properties of convergence and optimalities. Okay, so having my problem, here's how I make the updates. At each time step, each person minimizes their own price. They look at the price with their neighbors and see if they are reaching consensus, and then they see how the grid is affecting their pricing. And then we do something that everyone assumes normally, is that everyone talks to everyone else, shares their current time steps pricing vector around, and then we all kind of agree, like, where are we going to go from there? But of course, this is not great, right? You can't really expect to communicate so much for so long, especially when you try and scale this up. This is going to be very costly and not that great. So imagine a simple model here where you have a 2-node, 3-phase circuit, and let's say you have 50 customers on each phase. They all have to communicate to at least another 149 people each. That's 149 messages sent and received. It's a bit too much, even on a simple model. So how do we fix this? Well, let's look at the message that was broadcast last, and then we'll take the difference between that and our current update, right? So the essential idea is if at each time step, you do your computations and you process stuff, but if it turns out that your new pricing changes by 1/1000th of a cent, it's not really that relevant to computations. At that point, rounding error is more significant. So we're going to take some exponentially decreasing threshold, and if your update is not above that threshold, we're basically going to say that you don't communicate, okay? So now each update happens with the last broadcast message instead of your current states. And you only transmit messages if you are having a significant update. Fantastic. Okay, so where can we go from here? This is a simple idea. Let's see its implementation. So here's a simple experiment where, again, it's It's an ideal representative case of an unbalanced distribution grid. I'm taking a simple model here. In the solid curve, you have what your voltage profile looks like without any coordination. In the curve with the triangles, you've got a standard benchmark approach, and we can see that that already fixes our problem, right? It brings everything into where it needs to be. And then with the starred curve, you have the communication censored approach. Now, interestingly here, when you censor your communication and you try and reduce it, your voltages actually get closer to the nominal on average. So things improve a little bit. I'll talk maybe a little bit about this later, depending on time. Okay, so firstly, we know that the method works in achieving what we wanted to achieve. It stabilizes your voltages, brings them into your required levels. But now, what is the advantage? That comes from looking at your communication censoring pattern. So here on this curve, on this drawing, every white spot is when a customer sent out a message. Every black spot means that they didn't at 30 iterations of the algorithm. So this is, I think, in total about, 20 or 30% of the communication as opposed to, when you don't censor things. So when you have to pay for communication, that's quite a bit of savings. So that's good. Now you might be wondering, well, this is surely going to depend on the underlying communication structure. You still need everyone to be able to communicate to everyone, otherwise this approach doesn't really work. Not necessarily. So you could change to a different communication graph, where let's say now instead of everyone being able to talk to everyone, everyone can only talk to their next 10 or 20 neighbors, whatever it is. And you get a similar kind of result. So both algorithms, both methods work. And on average, so in general, the censored approach still brings your voltages closer to the nominal than the uncensored approach. And of course, again, with the communication censoring, you see again, having about 20 or 30% of the original communication requirements. Now, I don't remember what it is. It's in the paper. Okay, how am I doing on time? 2 minutes? Fantastic. Well, we rushed through that real quick, so thank you. But I'm going to come back, since I do have 2 minutes, to make some comments, which I wanted to. So let's see. Okay, I have a question for the audience first. How many PhD students are here? Just a show of hands. Okay, quite a lot. So here are some low-hanging fruits for the PhD students. Here we're looking at this sort of censoring between previous broadcast message and current state. You could also go and look at a different approach where instead of limiting the frequency of communication, you limit the frequency and the data, right? So that would just essentially be saying you truncate your Lambda updates at a certain point. Now, it's easy enough to see, if you read the paper and you read the proofs, it'll be easy enough to see that that approach is also going to work. You are going to converge to an optimal solution. But the tricky part there is figuring out the optimal level of quantization or truncation. So if you're a PhD student and you're free on a weekend and you have nothing better to do, think about that. How am I doing on time now?
I think it's all set now.
All set. 1 more minute? Okay, great. Now I'm going to give you another low-hanging but useful fruit that I think industry will appreciate. So if you want to work with industry, this is something that you should consider. Here I'm using a censoring threshold that is based on absolute differences using some exponential decrease. Of course, this is based on our dual parameter, which represents pricing. Now, you can imagine if I'm a poor, unfortunate PhD student who decides to buy an electric car, a pricing change of $10 might be the difference between me eating ramen and not. But if I'm a big building owner that's running this for a company, a pricing change of, say, $100 could just be meaningless. So one thing that you could try and change is here, look at a relative difference in the updates and do that in a distributed manner, and then figure out a way to get that to work. Now, again, it's easy enough to do. It's probably more than a weekend, maybe 2 weekends. but it is useful.
Okay.
Thank you.
Thank you very much, Abe. Questions? I have a question from Maria, please.
Oh, shoot. Okay.
Really interesting. So the first formulations, they are sort of well known in power industry, those formulations. I think that the question that I have is, you never solved the primal problem? Can
No,
you show,
no,
and the reason that I'm asking the question, you're talking about voltage, and the constraints are very nonlinear there. So is there any theoretical, this is for your weekend, any theoretical foundations to believe that these things would actually converge at the system level?
On the primal side?
Altogether, you have to solve both, right? You took the prices, they are price takers, but price is a result of, primal clearing.
I'm sorry, I'm not sure I understand the question, so.
Well, how do you create prices? By solving primal problem.
I mean, if you say so I'm genuinely not sure.
So
I'm not
you
the
pose
expert in
it
the
as
area.
dual and primal, right?
Uh-huh.
And then you concentrate on dual,
Yeah.
right? So what happens with the primal problem at the system level? That's the question.
Well, that stabilizes as well because you use a primal dual hybrid
Only for
convergence.
linear formulations, for convex optimization, for voltage is different, that's the question.
But this is a
Excuse
linear
me, excuse
formulation.
me. Yeah, probably you can leave the
Yeah,
rest
maybe
of
we
the,
should talk
of the discussion, the
afterwards,
panel at the end. Okay.
yeah.
Thank you, Maria. Thank you, Abe. Then we move on to the next paper. It's called the Cyber Physical Attack Leveraging Subsynchronous Resonance. The authors are Bozong Li, Baosen Zhang, and Daniel Kirschen. And Daniel will be the presenter. Please, Daniel.
So good morning. It's a great pleasure to be here and presenting some work. I want to acknowledge my co-author, Bozong Li, the postdoc who did the work, and my colleague at University of Washington, Baosen Zhang. So this presentation is a nice follow-up on the presentation of Philip a little while ago. So, excuse me, let's take the terrorist perspective to start. And what can a terrorist do? Well, terrorists could try to trigger a blackout. And if you trigger a blackout, well, you get headlines. That's good. But in a well-run utility, if you get a full blackout, fix in 8 to 24 hours, no long-term effects, essentially, once things are done. So really, from a terrorist perspective, if you really want to really do damage, you want to damage some of the power equipment. The more expensive, the better, right? So, because then you have a very large repair cost, it's going to take a long time to repair, and you're going to have a lasting effect. So that's really what the terrorist wants to do. So how do you get to damage power equipment? Well, you could try to use explosives or firearms, but to do that, you need physical access to the plant, not necessarily easy to do. You get one chance, typically, and you have a high risk of being caught. So not a great idea. So a much better idea is to use the energy that's in the system against one of its components. We have a tremendous amount of energy in the power system. Let's try to use it to destroy some of the equipment. So how can we do that? Well, we could try to get control to the cyber infrastructure, and that allows us to do this through some remote activity. So we can be safely somewhere in a friendly country and do damage in our enemies. And you can remain discreet until you have achieved success. So that's really a good technique. So what we try to do in this project is look at a possible cyber-physical attack scenario. So the idea was, well, we now have so many battery energy storage system, BESS systems in the system, and we could try to infiltrate the control system on one of those battery energy storage systems. And as people in the cybersecurity world say, the attack surface has grown tremendously because you have all of those, and many of them are from different manufacturers, so they all going to have their own vulnerabilities that we might be able to take advantage of. So the idea is, if we can get inside the control system of the battery energy storage system, that's the hypothesis I make here, we could try to modify the software to modulate the output of the battery energy storage system, so controlling the power that is being injected or extracted from the system. And we could do this in a clever way so that we modulate its output at a frequency that match one of the subsynchronous resonant frequencies of one of the generator in the system. So subsynchronous resonance, this is from one of the darker, less traveled corners of power system dynamics. So I thought I would give you a little refresher on that. Excuse me. Turbo generator, you have the low pressure, the medium pressure, the high pressure, the generator, the exciter, all on one shaft, right? And those are big masses on the shaft, which can be modeled as a spring. So you have a spring mass system. Now, as any good mechanical system, you're going to have resonant frequencies. In this case, there are going to be torsional resonant frequencies where some of the masses might start rotating against each other. And if you have enough of these little torsional resonance frequencies, well, you could create metal fatigue. Metal fatigue means after a while, the shaft might break. And if you don't believe me, if you go back to the 1960s or early 70s, I don't remember the exact dates, there were some couple examples where the shaft of large generators broke because of a resonance between series capacitances and these torsional resonant frequencies. So essentially what we're going to try to do is let's emulate that. Instead of having series capacitances, we're going to use the output of the battery energy storage system to do that. So essentially what we want to find is the resonant frequency of the system. So questions, can modulating the output of the battery energy storage system trigger one of those resonant frequencies? And does the resonant provide enough amplification to cause enough oscillation to create metal fatigue, although we did not look at the metallurgy of that? And then also, can we do it in such a way that the modulation of the battery energy storage system can remain small, so to remain undetected for long enough to create this metal fatigue? So I'll go briefly about the modeling that we did. It's just a bigger model where instead of having a single angular frequency for the shaft of the generator, you have a separate angular frequency and an angular position for each of the masses. And we are looking at the differences between the angular frequencies and the angles of these different masses, because that's really what's going to create the metal fatigue. We put that in linearized models where you have a bunch of those omega dots and theta dots variables, a big A matrix, omega theta, and then the forcing function where the delta L is the attack of the attack signals, the modulation coming from one of the load, one of these batteries that we model as a variable load. So we have some output variables, which are the angular frequency and angles that we measure at the generator terminal. And then we have some torsional variables, which are the variations of angular frequencies and angles within the shaft. And then we can come up with some transfer functions relating both the attack to the terminal variables of the generator, so things that the defender might be able to look at, and then the other transfer functions relating the attack to essentially the effect we have on the generator. And really what we are looking at is the ratio of these transfer functions, because at the top we have what's, I think I got it in the wrong way on this slide. The top one is really the internal, what's happening inside the generators. The bottom one is what you might be observed at the terminal generator. We want that to be as big as possible, because that way we make the maximum damage with the as little observable measures as possible, which is really what the attacker wants to be able to do to achieve metal fatigue. So a large value of this coefficient Rm is really what we want to achieve. So to test that, we looked at the classical test system from Grad Rogers, where we added a battery energy storage system here, where we modulated the output. And then we looked at the various resonant frequencies that we got from in this system. And then we looked at this factor Rm for the various, at various frequencies, essentially scanning to see where we get the biggest bang for our buck in terms of attacks. So this was done in the frequency domain. Then we also confirmed this with some studies in the time domain, showing that effectively, by modulating the output of the battery energy storage system, we could create those internal oscillations inside the generator. So that's where we stopped at this point. It leaves a few open theoretical questions. First, I have to admit we cheated. We cheated in the sense that we knew all the parameters of the system, so we could find out what those resonant frequencies were. So another question that remains is, can the attacker identify the resonant frequencies without having a perfect model of the system, which would be fairly hard to get, particularly if you want to have the masses inside of all the generators. And another open question from the defender's perspective is, well, can we detect these attacks? What kind of instrumentation, what kind of measurements do we need to get to be able to detect that somebody is doing something inside the system, and where is it coming from, and what attack it could be done? So I'll leave you with some countermeasures. This is in response to one of the comments from one of the reviewers. Could you defend against this? Well, for that, we went back to what people did a long time ago when they first looked at subsynchronous resonance. They said, what can we do against subsynchronous resonance? Well, it's the same thing. You start with prevention, and as Philip pointed out, the best thing to do is good software practice. From a power system engineer, that's pretty boring, but that's the best way to defend. You keep the attacker outside of the control system. Next thing you can do if that fails is, well, detection, trying to figure out that something like this is happening so you can actually do something about it. And then if you detect it, you can react. Well, best way is to disconnect the attacking battery energy storage system. And there's an interesting thing I found out a few weeks ago. There was an incident, I believe, in Southern California when the control system of a battery energy storage system started misbehaving and started creating oscillations in the system. Well, the operators were able pretty quickly to detect where it was coming from and disconnect it before these oscillations created problems in the system. And if that doesn't work, you might want to disconnect the affected generator before it's damaged. Finally, there are possible mitigation measures, but that would get really expensive with specialized relaying, filtering, or damping. So that's what we did. We thought it would be interesting to figure out what type of attack could be done to damage generators.
Thank you, Daniel, for a very good presentation. Some questions from the audience? Oh, yes, João, please.
So, thank you very much for the interesting presentation. As you said, the key issue here is for the attackers, is to know about the parameters of the system in order to identify the frequencies of resonance. But if they don't have that, and for sure they don't, wouldn't it be possible to try an approach that is capable to sweep the different frequencies in that battery, because now what you brought to us is that the problem exists. It can happen. So wouldn't it be possible? I would like to hear your opinion.
Yes, I think that's what we have in mind, is the idea that the attack could try different frequencies and then see if something starts resonating. But we haven't really looked yet whether it's actually possible for the attacker to detect that it's actually getting a response without being noticed by the system operators.
Okay, thank you. And then this brings us to our last paper. The title is Cyber Resilient Frequency Control of Power Grids with Energy Storage Systems. The authors are Jairo Giraldo. Close enough? Yeah. Good. Okay. And Masoud Parvania. They are with the University of Utah, Salt Lake City. And then Jairo is going to present the paper. Please, Jairo.
Good morning, everyone. Thank you so much for staying here for this presentation. My name is Jairo Giraldo. I'm part of the Utah Smart Energy Lab at the University of Utah. Today I'm going to present the cyber resilient frequency control for power grids with energy storage system. As we have heard with all the previous presentations, we know that communications networks are very, very necessary for improving the efficiency, the response, and the modularity. Oh, sorry, I think it didn't change. Yeah, it's not changing. Yeah, I think it's stuck. Sorry. So I was saying, we know that the integration of communications and monitoring and communication networks improves the efficiency of the power grid and enable us also to harness all the benefits of energy storage, renewable energy resources, distributed energy resources, help us to have like a fastest response, efficiency, and even modularity in the system. However, as we have heard in all the previous the grid presentations, it makes the power grid vulnerable to cyber attacks. Something that we have also we have heard from all the news and the latest cyber attacks is that attackers are becoming more sophisticated, more motivated, and they are now becoming more resourceful. So we really need to find strategies that help us to guarantee resilience and safety in the power grid. So there have been a lot of work that focus on the design of very specific attack scenarios. For example, we have seen a lot of work that focusing from the IT perspective, or some other works that focus on very specific attacks, from denial of service attacks, false data injection attacks. And also we have seen that there is a very broad literature that focus on attack detection. So there is a lot of work in detecting attacks, but unfortunately, a lot of these attacks are detected after they have affected their system. And actually, from our review, we haven't found like any mechanisms that can guarantee that the system will remain safe even when the attack is successful. So one of the things that we want to propose is a novel security mechanism that guarantees that any attack, any cyber attack that affects the frequency control, even if it's a false data injection attack, denial of service, reply attack that affects the control signals, that affect the sensor signals, we can guarantee that the system remains operating in safe operation states. So let's consider this like very typical example of frequency control in the power grid. So we have our synchronous generators, we have some energy storage, And we know that the frequency deviation evolves over time depending on the inertia of the system and in this very typical linear representation of the power grid frequency control. We have our primary controller, and we have the AGC controller. So in this case, we assume that the AGC is able to take the frequency measurement, and it's able to compute the necessary control commands to be able to control the synchronous generators and energy storage. Also, but however, a cyber attacker could intercept, as we saw in the previous presentation, the cyber attacker can intercept these control signals or these sensor measurements, and can tamper these measurements and like inject maybe a very particular type of attack, any type of attack sequence that can drive the system to unsafe states. Also, an attacker could modify the control commands directly and also drive the system to unsafe operations. So what we propose is an additional security block, and a block that will complement the existing security measures, like detection and other measures, that we call resilient constraints. So the whole idea is that we find these very specific constraints that add this additional security, so that any attack that is in the system in sensors or in control commands is not able to drive the system states to unsafe states. So our whole idea is to be able to find this extra saturation in the system and impose this saturation so that any attack affecting the system is not going to drive the system to unsafe operations. So as we all know, we can model the frequency control in the power grid as a linear time invariant system. We use here a discrete time representation. Well, the states are the frequency deviation, the power generation, the governor, and all these different elements that can come in the modeling the frequency control dynamics. We assume that we have a control input, so we are not going. Our analysis doesn't depend on a very specific controller, so we just assume that our control input is bounded. So these bounds comes from the physical limitations. We know that batteries can have a very specific limits in the amount of power that they can inject or absorb. The same synchronous generator, they have the very specific physical limitations. We assume that this omega is the uncertainty in the system, which comes from the load, which comes from the renewable energy resources, and we also assume that this is bounded, and we have a very good estimate of those bounds. Then we know that any attack in sensor readings or control command will affect directly the control input. So if an attacker injects some sensor, falsifies some sensor measurements, it's going to affect the control. Or if an attacker attacks directly the sensor commands, we are going to have, it's going to affect directly those control inputs. So our entire analysis is based on the reachable set. So reachability is a concept that has been studied a lot, particularly in control theory. And what we wanted to think it from the perspective of an attacker. So we define what we call the attacker's reachable set. So in this case, the attacker reachable set is all this set of states that can be reached by an attacker, by any sequence that an attacker can inject. So it can be any sequence. Usually, the analysis are done in assuming even infinite time. So the attacker reachable set is all this set of states that can be reached by any attack sequence. However, usually computing this reachable set can be very intractable when we assume that the control inputs are from a real set. There are ways to estimate this reachable set using ellipsoidal approximation. As we heard before, this is very nice because it's convex and it's a nice representation. And mathematically, ellipsoids can be represented just, well, I think this is just as a quadratic formulation where W is a positive definite matrix. So now we know that we can have or try to estimate this reachable set. But our goal is to see how that reachable set relates to the unsafe states of the system. So what we mean with unsafe states are all those states that are dangerous for the system. Usually all these states are known. So for just a good example is the frequency. We know that the frequency deviation has to remain in very specific bounds. Otherwise, the system is going to start failing. So we say So we can say that if the reachable set overlaps with the unsafe states, then the system is at risk. So we know that at least there exists any specific attack sequence that can drive the system to these unsafe states. So our main idea is to be able to find that the largest constraints that shrink that reachable set. So our whole idea is to try to reach to shrink that reachable set, so that it does not intercept anymore with those unsafe states. And then we can guarantee that, independent of the attack sequence, the system will remain safe. Typically, one way to represent these unsafe states is using hyperplanes representation. So in this case, we can, well, I think there are some issue here, but we know that we can represent it as the union of hyperplanes. So we can say, for example, this is an hyperplane. So all this area, we assume that this is unsafe. So let's say that if it's frequency, we assume that this is the minus 0.2 hertz. So we know that everything that goes below that value is going to be unsafe. So the same here. So this is just an example of how we can represent these hyperplanes. So this is just a very simple representation of defining these dangerous states. So our whole idea is to try to find that ellipsoid that doesn't overlap with these dangerous states. And to do that, we can also take advantage of the distance of an ellipsoid to a hyperplane, which is a very common mathematical representation, where we know that if the distance is positive, then there is no overlap. So that leads us to our main optimization problem formulation. So the optimization problem, the idea of this problem is to find the largest constraints. And why the largest? Because we want to guarantee that the system still can operate normally. And to find those largest states so that the reachable set does not overlap with the dangerous states. And I'm not going to go into the details of the optimization problem. They can be found in the paper. But the main idea is to solve this linear matrix inequality. So this particular constraint, what it guarantees is that the ellipsoid, that we can find that minimum ellipsoid that contain the reachable set. And these other constraint guarantees that the reachable set, that ellipsoid, doesn't overlap with the dangerous state. So by solving this convex optimization problem, we are able to find those constraints. I'm going to show with some examples. So just as a case study, we're going to consider this single area system. So we have a synchronous generator, we have two energy storage systems, and we are going to consider attacks in sensor measurements and attacks also in control commands. So this is some of the results that we obtained. So the first thing I want to mention is that this is the case without any resilient constraints. So this is just some the typical intrinsic constraints that the system, that the synchronous generators and the batteries and energy storage already have. And we can see that, and we consider an attacker that is able to compromise all the AJC control commands. So we are assuming like very worst case attack scenarios, which maybe some people might think that they are not feasible, but we always want to focus in the worst case scenarios. So if we are able to secure the system for these scenarios, then we can guarantee that any other attack will also be secure. So in this case, we can see that the random attack, an attacker that just injects some random values, is able to take the frequency to very dangerous levels. Here we also compute some optimal, we call it the optimal sensor and AJC control, which is just solving finding the attack sequence that maximize the frequency deviation. So in this case, we can see that for the AJC attack, we can find that frequency and that sequence. And this is just a projection of the system states. And this is the estimated ellipsoid. And we can see that the states for some random attack, they overlap with the dangerous states. But now when we use the resilient constraints that we found, so we found that these are the resilient constraints, but solving that optimization problem. And here we can see that for the same random attack, now all the frequency deviation remains bounded. And there does not exist an attack sequence by solving the optimization problem that can drive the system to a dangerous state. So in this case, and something that is interesting also is that even when we have, in this case, we have an initial condition of 0.1, we can see that the system still can drive the frequency regulation to 0, and the attack starts in 0.5. So before the attack, the frequency deviation is driven to 0, which is what we want. So we can see that the constraints do not affect the normal operation of the system. Even though we are imposing smaller constraints, they don't affect the normal operation of the system. And this is just the representation. As we can see, the ellipsoid that we found doesn't overlap with the reachable, with the unsafe states, and hence all the trajectories remain always bounded inside that reachable set. So just to conclude, we can see that we can solve a kind of simple optimization problem, which is offline, and we can find those resilient constraints that guarantee that the system will remain safe, even if the attack is successful. So, and we are considering like very powerful and worst case scenario of attacks. The results also show that the resilient constraints, that without these resilience constraints, an attacker can drive the system to unsafe states. But with these constraints, we can limit the impact of these very powerful attackers. And I just want to mention that this design methodology can be applied to other linear models of the power grid. And I just want to mention that this is part of many of the projects that we work in our lab, the Utah Smart Energy Lab, and I invite you all to take a look to the different projects that we work. Thank you so much.
Thank you, Jairo. Questions? There's a couple of questions. Well, I think you're the first one. The other ones, we have opportunity to put the questions for the presenters later on. Go ahead.
Thank you for the presentation. It seems like for cyber attacks, there could be like any possible number of combinations.
Please speak closer to the mic.
Is it on?
Is it on?
Yeah.
Or maybe it's not.
Yeah, no, thank you so much. Yeah, that's a very good question. And yeah, in fact, the whole idea of using this reachable set is that we can consider like any combination and any attack trajectory. But as you mentioned, yeah, there is going to be like a trade-off at some point. So at least with the simulations and the results that we had, we didn't have any issue in terms of guaranteeing that the system will operate normally. But yeah, probably depending on the system, we might shrink the ellipsoid like so much. And that's part of the future work that we are thinking is including also some additional constraints that guarantee that the system will still operate, and trying to find that trade-off that you mentioned. Yeah, that's a very good comment. Yeah, that's a very good point. Thank you. Yeah. Okay.
Okay, then we go to the second part of our session, and we invite all the speakers to come to the podium here. And then we have a Q&A session. Okay. Okay, then are you all set? Almost? Okay, please, when you wait to ask your questions, please state very clearly your name and to whom you are addressing your question, okay? Claudio?
Thank you. Claudio Canizares, University of Waterloo. This, can you hear me? Okay. Yeah, because maybe I have to speak really closely. Not a good thing in COVID times. My question is a comment general to the panel. I'm no expert on cyber attacks and cybersecurity. However, I see a lot of papers in the TSG, I'm a EIC, more acronyms. And my question is generic in the sense that always when I see these papers, I wonder two things. The first thing is, well, how difficult it is for a random attacker to attack a transmission system network, where you have all these private networks and access to the system is really limited, unless you are really an state agent in which you really physically get into the communication system. And my second question is, now we're talking about all these DERs spreading around and starting talking in the future, not yet, but in the future, talking with the transmission system and maybe affecting the behavior of the system. However, even in that case, which is a lot easier to access for somebody sitting in a basement somewhere, it would have to be a very coordinated attack. So still you need a very intentional and state type of actor to be able to actually affect the system. Could you please, these are questions I've been always wondering about, and would appreciate your comments and views on all these particular issues. Thank you.
Thank you. So whoever feels at ease to answer. Jairo?
I can answer to that. Well, from my, I'm not an expert like in hacking or cybersecurity, like specifically the implementation part, but something that I know is that attacking like transmission system or distribution systems is fairly difficult. Especially, as you say, you need to gain access to the system. You need to get access to. You have to have a lot of knowledge about the devices, the system, but also something that the history has shown, starting from the cyber attack in Stuxnet and the Ukraine, is that attackers are motivated and resourceful. So they might have maybe not one hacker in a basement, but they might have like hundreds of people coordinated, like trying to find these vulnerabilities and these weaknesses in the system. And so I think that what makes this topic a little bit scary is because even though maybe we haven't seen that many attacks right now affecting particularly the US, because I think there are still like very good security mechanisms. I think at some point we are going to start seeing more and more because attackers are more motivated, and there are so many motivations, not only money, but just the fact that they want to harm, and they have the resources. So there are so many resources, and it's not only one person. It's usually like groups of hundreds of people that are just being paid and sponsored to find these weaknesses on the system.
Okay. Yes, Philip.
Yeah. Is that on? I don't know.
It's not on.
It's on the thing. Okay, now it's on. Yeah, I totally agree with my colleague. So don't think about one hacker sitting in a basement somewhere. They have resources, they have money, and usually they also have time. Regarding your second question about the DERs, I want to say for these DERs, usually they are not only connected to a control system of a grid operator, you might also imagine they are connected to other entities. For example, VPP operator or smart home system, so their attack surface is even higher. So that's why they might be a target in future scenarios, because for some reason the attacker, for example, can also compromise smart home systems or something else. It's not always the very safe system of the grid operator, so to say. It could also be other ways to get into the control of the DRs.
Okay, anybody else would care to make a comment?
Just have a follow-up. Yeah, follow-up question, Gregor Radovich, University of Sydney. So I will follow up on Claudio's question. I'm also not an expert in cyber physical systems. Is there anything we can learn from other communities or other industries, for example, banking? Are there any lessons that they might have experienced in the past that might be useful for us? That's coming from a total non-expert.
Well, I think, there are different levels. There's a level of keeping the intruders out, and I think there are plenty of lessons to be learned there on good software practices, and I think there's a lot of exchange of information at that level. I think where we can contribute something is where we are different. It's where you get into the physical system, where the impact of the attacks, if it does happen. I think that's different, and that our system is pretty unique in that respect.
Thank you, Daniel. Anybody else would care to comment on that? Philip? Yeah?
Yeah, usually if you think about banking, so the attacker tried to get into the IT system of the banks. Like this first step is usually also quite similar for these attacks on industrial control systems or power systems. So they try to get into the IT system first, maybe with a phishing mail or something, and then they propagate. And at least for some of the already happened attacks, they then propagated into the OT systems and into the control systems. So these steps, they are in addition to that what's actually happening there. Yeah, so, and then, of course, then the attacker is able to have some impact on the physical system, and that's we want to avoid. And I think we have to address that like in a holistic approach, that the power system itself is always intertwined now with the cyber system. So we have to make the total system like resilient against this kind of attack.
Thank you. More questions from the audience? Oh, over there, please. Yeah. Oh, okay. You go. You go. You go. Okay. It's also a tie, I guess, but. Okay.
Actually, it's working now. Great. Okay, so yeah, luckily we have two mics. I'm Lina Roald from the University of Wisconsin-Madison. I just had a question, and that was about sort of secondary effects of implementing these type of both detection and also prevention. I mean, Navav mentioned about the possibility that this reachable set, for example, gets so small that you can get a high-cost system operation. But I was also wondering if it's a concern that, for example, the system would no longer be able to respond to a large generator outage, or in the case of the best systems, if you have to disconnect them, could you then start something where you lose all your reserves? Or, I don't know, I was just wondering if anyone had thoughts on kind of these sort of secondary effects of actually responding to a cyber attack that kind of could cascade further.
Okay, I think Jairo is the one to
Yeah, thank you for the question. That's a very nice question. Yeah, so definitely there is a trade-off in terms of some of these security and resilience mechanisms can have an impact on the system. So I think that's yeah. So there is definitely you have to take into account exactly what you want to guarantee from your system in terms of operation. And I think one of the solutions to these kind of things is to start connecting different aspects. So for example, that resilience methodology that I presented may be something that you don't need to have all the time, but probably you can link it to some detection mechanism. So once there is an attack or you are sure there is something happening, then you will activate kind of that defense. So you can start doing those type of connections. So that's why I mentioned that this is they are like this complementary. So detection, mitigation, resilience, all these are complementary things. But yeah, there is definitely a trade-off that you have to be very careful when you are designing these systems to guarantee that you, how much do you want to sacrifice in terms of operation to guarantee resilience? So there is always going to be a trade-off that as part of the future work, at least in my case, we want to start thinking also about those operating points that we want to guarantee in the system.
Okay, any other comment from the authors, the speakers? No? Then, gentleman there, okay. It's working now? Oh, okay, good.
Hi, Misha Chertkov, University of Arizona. I wonder if it may have a sense for attacker to wait for extreme event, and we now have so many of those. Let's say we have, recently heat wave in Europe, and there are always some emergency. And many of those emergency put a lot of stress on distribution. We haven't heard yet about feeder, fault-induced delay voltage recovery associated with those events, but potentially electric cars, very few of them can initiate. That's maybe an example. So can any of you comment on, on this perspective. So if I would be attacker, I probably would wait and not launch it only in a case when there is an opportunity.
You would wait for vulnerable
for system to be stressed.
Okay.
Well, that's common sense, right?
Yeah.
And I'm not sure I heard from any of you discussion of that.
Then you want to comment? Yeah.
What would you say?
Yeah, on the one hand, you may say, yes, the system is more vulnerable and then your attack may have a higher chance of succeeding. But then when the system is under stress, the operator is very alert and ready to react. If everything is nice and smooth and happy, the operator may just relax and not really pay attention. So there's a trade-off there too.
I agree, but we are talking about distribution. And as we know, operators don't really know what is happening on the distribution. Especially, so there are scare stories about lack of visibility, right, for operator.
Anybody else want to comment on that? Philip?
Let's try to comment on that. I think if you think about this multi-stage cyber attack, the attacker is somehow free when he wants to launch the last stage, so to perform his actions in the physical system. But it's not that clear if the attacker has all the information then to wait for, or to know that the system is stressed or not. Maybe he has that information and then he might target that situation to add something on top that the whole system breaks down. But, I mean, possible, but not necessary, I would say.
Well, if it is hard for 2 weeks in Europe, right, you know it's under stress.
Okay, let's move on to the next question. Please. Oh, okay. So let him. You are going to. You are going to ask the question yourself? Oh, okay. Mladen, por favor.
Yeah, Mladen, Kizuna, Texas A&M. You know, I am always wondering, listening to papers like this, what really matters in these attacks. Of course, the system is vulnerable at that point in some fashion. But the outcome of all of this is, are the customers or the consumers going to be affected? And is there a price issue that you mentioned, Daniel, you know, a major damage that costs a lot of money? So how do you put your approaches in the context of impact on the end user? And you know, the impacts are quite relevant, because if a few houses lost power for 10 minutes, 15 minutes, an hour, whatever, that is insignificant. But if they lost power for days, it becomes an opportunity for many other things to happen, because there's a social distress at that point in time. So that's one part of the question. The other part is how any one of these attacks may create chain of impacts on other infrastructures. For example, I use this example because it's recent. In Texas, when we lost power in February 21st, out of 21 million electrical, we lost about, I think, 4.5 million, but we lost 12 million water customers, meaning they didn't have clean water to use. So are there any chain impacts of what you're talking about on other infrastructure? So two-part question. One is impact on the customer. Can you project somehow whatever the impact on the grid that you're discussing is causing over to the customer? And the other one is the impact on other critical infrastructures. If you can put it in this context of your papers, if you cannot, maybe you can comment in general about this. Thank you.
Okay. The speakers want to comment on that?
Well, we didn't really look at it in those terms. We just were looking for a significant attack. But I think, Mladen, you put it in really important questions. And I think all those attacks should be considered in the framework that you described.
Okay, then we'll go to the next one, please.
So my question, my name, I guess, is Mas
identify yourself.
Masauki, University of Vermont. It's my first IREV, and I'm really excited to be here. And thank you for your presentations. When it comes to cyber-physical systems, often data is really important and actuators are really important. And so a lot of your presentations dealt with voltages and EV charging, dealt with synchronous subsynchronous dynamics and battery controls. And they tend to be different actors who have access to different information. So what role do the different actors play and the different layers of information? Because I think a lot of your works assume that you have access to everything. And I know, Daniel, you mentioned that you're cheating because you have access to the models. But what role do these layers play? Because the real world, an attacker or a defender does not have access to everything. So that I'd be interested in your viewpoints on the asymmetry between data, information, and control. Thanks.
Okay. Daniel, you want to comment on that?
Well, there's the old, security to obscurity approach, but as somebody pointed out, attackers have time and resources and motivation to try to get through that. So, yes, they may not have access to all the information, but, these days they come up with smart techniques to try to get to the data that they might need. That's, I think, a classical intelligence problem. Sorry, can't add much more than that.
Jairo?
Yeah, I just want to add that I guess these different layers will make it harder for an attacker to start maybe designing more sophisticated attacks. But also the problem is that since things are connected somehow, especially right now, and unfortunately there are a lot of not good practices in terms of separating certain networks, separating certain IT from OT. I think that could even be a way that an attacker can penetrate a system, starting from like he was saying, like a phishing attack that will then go to the physical aspect. So those layers can either limit or can also be the bridge, so that an attacker can actually be successful. And unfortunately, attackers are very smart. They will always try to find different ways to access and bypass all these different layers.
Okay, Ian, please.
Okay, Ian Hiskins, University of Michigan. I got actually 3 comments or questions or something. The first one's for Daniel. So Chris DeMarco did a bunch of work a long time back using eigenvector design to coordinate generators to do exactly what you have proposed of breaking shafts. And then more recently being 10 years ago, he extended that work to look at load control and how you could coordinate control of loads to break shafts as well. The first work led to Prabhakunda being aghast that anyone would even consider the possibility of studying work that would be of such obnoxious outcome. But anyway, there was some interesting interactions back there. I guess the next point was to say, okay, where does one find vulnerabilities these days? There's a vulnerability right there.
Turn off. Okay. Go ahead, Ian.
Yeah, so I'll finish because that's clearly a wind-up signal. There's a great vulnerability in wind turbine gearboxes, and they break because of the mechanical stresses. But the question arises, what could you do on the electrical side? Are there possibilities for signals that you could inject on the electrical side that could put stresses on wind turbine gearboxes? And then you could, then there's a motivation because, if you can break everyone's gearbox in a certain wind farm, you can gain more market share. Those kinds of things happen. And my final kind of comment, there was work done at ETH some years back, looking at signals injected into the AGC system to do bad things on the system. And from memory, the counter to that was to look at signatures. And so injected signals had signatures, the characteristics were different to normal behavior. And so it gets back to kind of the machine learning idea of if you can learn what normal behavior is and then identify abnormal behavior, that's maybe a mechanism for preventing those types of interactions. I think the project was called Viking. It was a multi-university, KTH in Stockholm, ETH in Zurich, but there was a bunch of work done on that.
Okay.
I'll say, Ian, you're even more devious than I am. Gearboxes, I should have thought about that.
If you own solar farms, you want to break all the wind farms.
Anybody else to comment on that? No, then we go to next question. Yourself?
Since I'm the only one walking up. Hi, Andreas from RWTH Aachen. I have a question on the subsynchronous resonances. You said, Daniel, well, the trick is for the attacker, the trick is to do it in an unnotified way, and for the plant operator, the goal is to detect that these subsynchronous oscillations happen so that the torsional stress is there. So I would assume if these large masses rotate against each other, there should be some change in the noise level and in the vibrations in the machinery. Would that not be the best way of identifying that torsional stress is happening?
I suppose there might be techniques like that. I don't know enough about that aspect to really be able to comment validly. I suppose there might be techniques for doing that.
Okay, yes. Because that's sort of my experience when I visit these plants, that the technicians there, they listen to their machinery quite a bit of times because it often is the best trigger for identifying that something is not right. Yeah. And then, well, picking up on Misha's term, so attacking the system when it's already in a critical state. So you said for the defendant, if such subsynchronous oscillations happen, the best thing would be to shut down the plant. But what if this plant is critical to system operation because it provides ancillary services? I mean, that would be quite a nice strategy to, not do anything for a long time until, say, primary frequency control is a need, and then at that moment making sure that certain plants are not available. Yeah.
Absolutely.
Yeah.
Yes.
Okay. Yeah. We cannot tape you. Yeah,
So
please.
Yeah. You said adaptive control. Yeah.
I really think it's an important comment that you're making, but we cannot wait, let's say, to have these subsynchronous oscillations for the operator to decide what to do. So, yes. So I think the whole area of getting next generation primary control to be a little smarter to recognize these things. Eric Allen, some of you may know him, he used to work for NERC. He did his PhD thesis, master thesis at MIT several years ago on adaptive feedback linearizing control to cancel out the subsynchronous resonance. And the controller does it. You don't have to rely on protection. So I guess putting that in context of cybersecurity is a different question, but I think, Daniel, there is a state of art where you can rely on smarter local controllers to identify these. And so that was my comment. Yeah.
Okay. I would add a comment to that, Daniel. As you said, it would take a sort of a long time for an attacker has been successful in his intent to create a subsynchronous resonance that is fatal somewhere. But then generating units, they go through regular or periodical maintenance. So, it's possible that your work could just add to recommendations for this routine maintenance, maintenance routines actually, is to look at signals or vestiges of torsional effects that could then try to identify that the attacks were being made, and then after that you could maybe have countermeasures. How do you think?
Well, I think if you can start seeing the effect of metal fatigue on the shaft of a generator, it's too late, right? Damage has been done, and you have to replace the shaft, and there you go, a few $100 million. So better to do it before that.
Okay. Well, Patrick, please.
Yeah. Yes, it's my turn perhaps. So Patrick Panciatici from RTE France, so this is a TSO for France. So we are very at the system level and we try to understand all this interaction. Okay. And so for me, cybersecurity is very interesting, but it's just a new motivation to be robust. Yes, and for this subsynchronous, of course, we have a lot of concern about that, and we have some controls that try to damp all this synchronous, subsynchronous oscillation. Because we have already some people that are injecting, yes, we have a lot of power electronic everywhere. So even if it's a more random process, but we are not managing to be able to control anything, everything. So we have a lot of attackers, also users of the grid. So I don't know, so it's kind of, and perhaps we need to have some grid code that prevents something, but it's not possible to do some grid code in frequency domain, for example, because the lawyer don't understand what is frequency domain. But anyway, so my question was more that it's good to be robust, and if we have some money from the cyber dimension to be more robust, I think is a good idea. But the problem is always to find a trade-off. Yes, there is always something that there is no free lunch. So if you are doing something, you are losing perhaps something. So no, I don't know. You are less agile, or you are more, I don't know, more conservative. So I don't know. There's not enough for us trade-off in all the discussions that we have, and also we have to remember that we can have a lot of physical attacks on the asset, and perhaps it's not a bad idea to put more software solution to be robust or to detect this physical attack. So for me, this is a lot of question about trade-off, and perhaps we can comment on that, how to find the right trade-off. And it was the case of course, if I shrink sufficient mistakes to nothing, then I'm very robust, but I'm not. The service is not anymore there, so
okay.
This is kind of
okay. Please, a very brief answer or comment, because we're running out of time now.
Well, yeah, I guess the answer probably will be very similar to the one that I did before. So, yeah, as you say, the trade-off is a very important part, and I think one of the ways to address that is to connect, as I mentioned before, to connect with different other detection and other things, maybe some machine learning strategies that help you to know what is the operation mode of the system, and then you kind of design a very specific defense for very specific operation modes of the system, so that you can kind of make your system a little bit more robust without compromising the normal operation.
Okay, so I think we ran out of time, so we just want to let us give a round of applause to all our speakers. And then we adjourn the session. Okay, thank you very much.